Welcome to this comprehensive end-to-end tutorial on Reconfigurable Intelligent Surface simulation at 28 GHz. We begin our workflow with a single unit cell model fully constructed within the Ansys HFSS environment. To properly isolate and define our simulation boundaries, we right-click the workspace, navigate to Create Open Region, and set our target operating frequency. The operating frequency is specified at this stage to ensure that the radiation boundary is automatically sized according to the electromagnetic wavelength of interest. By changing the padding type from a percentage offset to an absolute offset of exactly 0 millimeters, we establish the base boundary context for our unit cell analysis. With the bounding airbox successfully generated around the geometry, our next crucial step is to define the periodic behavior of our infinite array. By choosing Auto-Identify Lattice Pair, under our boundary assignments, the software automatically detects and maps the periodic network coordinates along the global XY plane. This critical automation step establishes the primary master and slave spatial relationships required for accurate Floquet port analysis. The generated lattice vectors provide a visual confirmation that the periodic boundaries have been correctly assigned on the unit cell walls. These vectors define the repeating directions of the structure, allowing a single unit cell to accurately represent an infinitely large RIS array. By leveraging periodic boundary conditions, we significantly reduce computational resources while preserving the electromagnetic behavior of the complete surface. Next, we assign our wave excitation. Selecting the top face of our newly defined airbox, we right-click and choose Assign Floquet Port. Within the Setup wizard, we manually map out the lattice coordinate directions. These lattice vectors define the periodic reference frame used by the solver to characterize the propagation of incident and reflected electromagnetic waves across the surface. By clicking Define and snapping vectors A and B directly to the corresponding outer vertices of our geometry, we explicitly link the electromagnetic port excitation to our unit cell's physical orientation. Accurate vector placement is essential, as it determines how the Floquet modes are referenced throughout the simulation. This ensures that the incident wave interacts with the periodic structure in a physically consistent manner. With the Floquet port fully configured, the model is now prepared for the excitation and analysis of electromagnetic wave propagation through the RIS unit cell. We advance through the remaining default setup wizard options to complete our primary Floquet port initialization. To accurately simulate our reconfigurable element, the integrated tuning diode is represented as a lumped RLC boundary condition. This enables us to dynamically evaluate the surface's electromagnetic agility by toggling between its on and off electrical states simply by altering the internal resistance, inductance, and capacitance parameters. In this initial configuration, the diode is set to its baseline off-state equivalent circuit, providing a reference point for subsequent performance comparison. By modeling the device with lumped elements, we can efficiently capture its switching behavior without introducing unnecessary geometric complexity into the simulation. Before launching the full electromagnetic solver, we execute a rigorous validation check under the Simulation tab. This steps through our 3D design, boundaries, excitations, and mesh link setups. With all design variables successfully validated, we can confidently click Analyze All to initiate the high-frequency electromagnetic sweep across our targeted band. This pre-simulation verification helps identify potential setup inconsistencies before computational resources are committed to the solve process. Once the analysis begins, HFSS calculates the electromagnetic response of the array's unit cell and generates the data required for subsequent performance evaluation. Once the processing phase wraps up, we move to data analysis. We generate a new rectangular solution report to plot the phase of our reflection coefficient, $S_11, in degrees. By selecting the angle degree function and placing a data marker at our precise operating frequency of 28 GHz, we extract our baseline phase response. This completes the assessment of our first operational state. Now we pivot to modeling the unit cell explicitly in its active tuned on state. By accessing the lumped RLC boundary properties assigned to our tuning slit, we update the values to match our forward biased pin diode parameters. We deactivate the capacitive variables, assign a low forward resistance of 4.2 ohms, and input a parasitic inductance of 0.05 nanohenries. These equivalent circuit parameters accurately represent the conductive behavior of the diode when forward biased, enabling current flow across the tuning gap. This state transition fundamentally alters the electromagnetic response of the unit cell, allowing us to evaluate its reconfigurable performance and phase shifting capabilities. With the material profile configuration locked for our active state, we verify that our periodic boundary conditions and Floquet port mappings remain fully intact. A quick pass through the validation checker ensures complete model health before we push our updated state variables back into the Ansys HFSS solver engine. Once validated, we launch the analysis to compute the electromagnetic response of the RIS unit cell under its forward-biased active operating condition. Once calculation wraps up, we return to post-processing to evaluate our phase characteristics. We generate a fresh rectangular data report, plotting the return loss phase response across our frequency sweep. By placing a data marker at our 28 GHz center frequency, we extract an absolute response of 137.5 degrees. When mapped against our previously extracted data of -41.5 degrees for the alternate state, it confirms that our desired wideband phase delta of 179 degrees has been perfectly achieved. This substantial phase separation demonstrates the effectiveness of the reconfigurable design, validating the unit cell's ability to provide near 1-bit phase control for intelligent surface beam steering applications. Validating individual unit cells gives us the foundational building blocks required to scale our architecture. We move from single element validation up to a complete 64-element, 8x8 explicit reconfigurable intelligent surface model. Using synchronized phase state switching patterns mapped dynamically across this full matrix, we can precisely control and redirect incident electromagnetic beams, unlocking next-generation beamforming and smart environment capabilities for future wireless networks. The resulting array demonstrates how programmable electromagnetic surfaces can intelligently manipulate wave propagation in real time, enabling advanced wireless communication and sensing applications.